Okay, guys, this is the last video for Chapter 3, and we're going to look at a couple of other concentration units beyond molarity that you might hear about in different applications, and then we'll do some calculations with these. So here I just listed all of them. Okay, so one unit for expressing concentration of a solution is the mass percent. Okay, and so it's useful when you can't calculate the number of moles of solute, perhaps because you don't know the molar mass of your solute. That's not uncommon in chemistry. And so the way you calculate a mass percentage is you take the mass of the solute, divide it by the mass of the solution, and then you multiply that by 100. And that gives you your percent mass. You can do the same thing, but by volume, okay, which is sometimes useful for both liquids and gases. So, for example, if your solute is a liquid or a gas, you could take the volume of the solute, divide it by the volume of the solution, multiply by 100. That's the percent volume. Another one that we see in different settings, medical settings here, the mass volume percentage. So you have a mass of solute divided by the volume of solution, and then you multiply that by 100. So it's a different kind of percentage in that sense. What you hear about in terms of environmental studies, you often will see the toxins listed, pollutants listed in parts per million or parts per billion, which is useful when you are dealing with very minute amounts of solutes, so very small concentrations. Here you take the mass of the solute divided by the mass of the solution, and then you multiply by 1,000,000, and that's what gives you the parts per million unit. If you wanted to work with the parts per billion, instead of multiplying by 1,000,000, you multiply that ratio by 1,000,000,000. And what this does is when the mass of the solute is very, very, very small compared to the mass of the solution, it just gives you a number that's a little bit easier to work with when you multiply by such a large number, either 1,000,000 or 1,000,000,000. Okay, so I think we just have some problems to work on, and so we'll just go through these. Here we've got a 5-gram sample of spinal fluid that contains 3.75 milligrams of glucose. They want us to calculate the percent by mass of glucose in the spinal fluid. Okay, so our percent mass is going to be the mass of the solute. So I'm going to write this as mass of glucose divided by the mass of the solution, and we multiply that by 100. Okay, so in this case, it's going to be 3.75 times 10 to the minus 3 grams divided by the 5-gram solution times 100. So I'm getting a percentage of 0.075%. The follow-up problem, part B, is identical. You just have different numbers. Okay, so, one difference here. Let me go ahead and work this one since there's a little tiny trick to this one. Notice that in the definition, here I'll go ahead and write it out. So for this one, we want the percent mass of HCl in this cleaner. You want to take the mass of the HCl and then divide it by the mass of the HCl plus the mass of the water, right? Because this is the mass of the solution, not just the mass of the water. You need to take into account the mass of the HCl as well. So that's the trick with this one, that they don't give you the mass of the solution directly. You have to actually calculate that. So we're going to have 135 grams divided by 135 plus 775 grams. And we'll take that times 100. And I am getting 14.8%. So this cleaner is 14.8% HCl. Let's see. Okay, there's another little trick to this one, so I'm going to go ahead and work this one out as well. Okay, so this is part A. So concentrated hydrochloric acid is typically 37.2% HCl, and we're going to take that as by mass. Okay. Now, they give us the density of the solution, so we know the density of the concentrated hydrochloric acid, and they want to know what is the mass of hydrochloric acid in the in a volume of 1/2 liter. And so this problem involves a little trick. Okay, so first of all, they give us the percent mass, and what they want us to do is to determine the mass of the HCl. We want to divide that by the mass of the solution and multiply by 100. Okay, so we want to rearrange this equation and solve for the mass of the hydrochloric acid. So that's one of the tricks. And then the second trick is that they don't give you the mass of the solution directly. Rather, you need to calculate it. And what we will use is the density formula, that the density of a solution is the mass of the solution divided by the volume of the solution. Okay, so they didn't give us the mass of the solution. However, they did give us the density and the volume, so effectively they gave us the mass. Okay, and so I'm just going to substitute that in. Algebraically, we're going to take the density times the volume of the solution. And that's going to give us the number that we want. So we'll take this 37.2%, divide that by 100, and then we're going to multiply by the density, 1.19 grams per milliliter, and then we'll multiply that by the volume of the solution, which is going to be 0.500 times 10 to the 3 milliliters. Okay, and that's going to give us the number that we want. And so I'm getting from that 221 grams. Let me check my math here. Yep, that makes sense. In the follow-up problem, what volume of concentrated HCl contains 125 grams? Let's see, we want to, so it's the same formula. I'm going to go ahead and rewrite it. So the percent mass is the mass of the HCl divided by the mass of the solution times 100. We will substitute in for the mass of the solution. We'll substitute in the density times the volume of the solution. Okay, so in this problem, we know the percent mass, that's coming from part A. We know the mass of the HCl, that's the 125 grams in part B. We know the density, and so we need to solve for the volume. So I'm going to rearrange this equation. and we'll have 100 divided by the percent mass. And so this is going to give us the volume that we want in units of milliliters. So the mass is 125 grams divided by a density of 1.19 grams per milliliter. And then we'll take that times the ratio of 100 divided by 37.2. So I'm getting a volume of 282 milliliters for that. Let's see. It looks like in this next problem they are asking us to consider percent by volume. So we're looking at a rubbing alcohol solution. That's usually 70% by volume. If the density of isopropyl alcohol is 0.785 grams per milliliter, so that would be the density of pure isopropyl alcohol, they want to know how many grams of isopropyl alcohol are present in 355 milliliters of rubbing alcohol. So here we're working with the percent volume formula, which is going to be the volume of the solute divided by the volume of the solution times 100. Okay, so they give us the volume of the solution, therefore we can calculate the volume of the solvent, and given that they have told us what the density of the rubbing out of the isopropyl alcohol is, we can use that to find the mass. So this is going to be the volume of the solute, and this will be the mass of the solute. So this is the density of the solute itself. So we will rearrange this equation and solve for the volume of the solute. I'm going to go ahead and do this in two parts. So we will do the 70% divided by 100 times the volume of the solution, that's the 355 milliliters. So I'm getting 248 out of that, 248 milliliters. That's the volume of the isopropyl alcohol in the rubbing alcohol solution. Okay. Now what we want to do is take that volume of solvent and take the density they've given us and solve for the mass of the isopropyl alcohol. And so we'll rearrange the density equation. It'll be the density times the volume. The density is 0.785 grams per milliliter. And then the volume is that 248. Giving us 195 grams. It looks to me like the the follow-up problem is very close to being the same, although there is a moles calculation involving the molar mass. But I think if you work through this problem, you could probably figure that one out. And so I'm going to leave part B as an exercise for you to try. And we're going to go ahead and look at the parts per billion and parts per million units. I just need to grab a little bit more paper. So here we're dealing with lead in tap water. And apparently the the threshold for needing to take remedial action is 15 parts per billion of lead in water, and we're being asked to calculate that in parts per million. So convert the parts per billion to a parts per million. And then they want us to do a calculation involving finding the mass in micrograms in a sample of water. So let's take a look at the parts per billion and parts per billion formulas. So parts per billion is defined as the mass of the solute divided by the mass of the solution, and then that's multiplied by 10 to the 9. And the parts per million unit, I'm going to put that right here, parts per million is the mass of the solute divided by the mass of the solution times 10 to the 6th. Okay, so these are the two equations. And what I'm going to show you now is a ratio trick. We are being asked to calculate parts per million from parts per billion. Watch this. Okay, I'm going to take the two equations and I'm going to divide one equation by the other. So I'm going to erase these equal signs, and I'm going to make that equals this. Looks complicated, but you can see that those parts factor out, and this simplifies to parts per billion over parts per million equals 10 to the 3. So if you wanted to calculate the parts per million from the parts per billion, you simply need to multiply it by 10 to the minus 3. So we take the 15 parts per billion and then divide it by 1,000. And that is going to give us our parts per million. And so we're going to write that as 0.0015 parts per million. In the follow-up problem, at this concentration, so at 15 parts per billion, what mass of lead would be contained in a typical glass of water that has 15 parts per billion lead? And we need to make an assumption here in part B. We need to assume that the density of this water is roughly the density of pure water, which is about 1.0 grams per milliliter. Okay, so that's something that we just need to kind of assume. So since we have 300 milliliters, that means that we have the mass of our solution is 300 grams. Okay, so that's part of the assumption. Then we can take our parts per billion definition and we can rearrange it and solve for the mass of the solute, which is going to be the mass of the lead. So we'll take our parts per billion and we are going to multiply that by 10 to the negative 9 times the mass of the solution. So this is going to be 15 times 10 to the minus 9 times that 300 grams. And I'm getting 4.5 times 10 to the minus 6 grams, which is equal to 4.5 micrograms. And so that's how you work with parts per million and parts per billion. I'll leave the follow-up problem to you as an exercise, and I think that's the last one, so we're going to stop this video right here.